Hello, my name is Angelica Torres, and I am one of the co-authors of the paper Theoretical and Numerical Analysis of Point and Line Incidences, which will be presented at the ICCB 23 conference. In this work, we study the joint image of incident points and lines, assuming a pinhole camera model. We use techniques from algebraic geometry to prove theoretical results on the joint image of two types of problems, either points that are incident to a line, like we see here on the left, or lines that are incident to a point, as we see here on the right. Our results are in line with previous algebraic results presented in these two papers, the Joint Image Handbook and Line Multiview-Varieties. Both works study algebraic varieties coming from the joint camera maps for points and lines. And by algebraic variety, we mean a set that can be described as the solution of a system of polynomial equations. Our first contribution is the definition of the anchored multiview varieties. The anchored point multiview variety is the joint image of points that lie in a fixed world line, and the anchored line multiview variety is the joint image of lines that go through a fixed point. The idea of using these varieties for triangulation is to take into account previous knowledge of incidence relations to triangulate better points or lines. For example, if we want to reconstruct collinear points, without taking into account the collinearity, we will get something like this, like we see here on the left, whereas taking into account the incidence relation will give us something like we see here on the right. So using the anchored multiview variety guarantees that the triangulated points are collinear. For these varieties, we provide a set of equations. For the point multiview variety, the first set of equations come from the fundamental matrices of the first camera with the rest of the cameras, and the second set of equations comes from the incidence relations that we want to preserve. For the anchored line multiview variety, the first set of equations are these determinants that come from the intersection of the back projected planes of the line correspondences, and this last set of equations also comes from the incidence relations that we want to preserve. Our second contribution is related to the error correction of real data. For both anchored multiview varieties, we compute the number of critical points of distance function from a noisy correspondence to its closest perfect correspondence in the anchored multiview varieties. These computations are theorem 1.7 in our paper, and the results that we get are these. The number of critical points of the distance function to the anchored point multiview variety for m views is 3m minus 2. And the number of critical points of the distance function to the anchored line multiview variety for m views is given by this polynomial of degree 2. Our last contribution is a set of numerical experiments comparing the process of triangulation and error correction of collinear points using the anchored multiview varieties versus triangulation of points with traditional methods. The experiments were done using homotopy continuation, and part of the results are here in these plots. We compare speed and accuracy of the triangulation for 2 and 3 views, and we see that in general, using the anchored point multiview varieties leads to a faster reconstruction while having comparable accuracy. In these plots, the bars that are depicted in blue correspond to the traditional methods for reconstruction, and the bars plotted in pink or yellow are the methods using the anchored multiview varieties. We see here that the speed with the anchored multiview varieties is better, and the accuracy is comparable to traditional methods. A complete explanation of the results is included in the paper and its supplementary material. We thank you for listening to this explanation, and if you have any questions, please do not hesitate to contact any of the authors.